Oh, good morning. I'm officially starting because I'm making a recording, and this recording will get posted in due time. Every podium, though, is different, and I haven't worked on this podium for quite a long time. But I'm old enough to say that I bought these podiums when I was on a team that bought this stuff, when our engineering department actually controlled the podiums, or our college did, and then eventually the campus took them over, and I'm kind of, in a way, kind of depressed that I still haven't replaced them or changed anything on them. But, you know, if you have stuff that you probably say it's really good, I bought it ages ago, but then you have other stuff that you think, I should get new stuff because this stuff's got issues. But I guess in terms of build, it's not falling apart too badly. So I'm going to go through a lot of the material that I have posted on the website, but I'm going to start on the website just to take you on a tour of it. And you can come in and grab a syllabus and check off your name. Check your name off on there and grab the sheet next to it. Then you can sit down and listen in. Your first name is? Bagheera. Bagheera? Okay. We will have an icebreaker time later when we start the second session. And if you're an undergraduate student, which many of you are, you're probably saying, why would we have an icebreaker? Or do you know what an icebreaker is? Does everybody know what an icebreaker is? Or not? So I like to do that so we get to know each other better, and we'll spend just a few minutes doing that. So what I was saying is I want to take you on a tour of the website a little bit, because it's going to be the point of contact for getting information for the course. Another point of contact, though, is going to be via Slack. And so here's somebody that just joined. Yeah, you just joined. So this is what I'm typically going to say to you if you just join. Just write back to you. But these are called direct messages, or I guess you guys are much better at this. You call them DMs, right? Some of you live your life on DMs, I think, right? I'm not saying it's bad, but Slack has that exact same terminology. But up here is another avenue for learning things about this class. And the history only goes back so far, but it is there, and it's just been rolling along for 2 years now. And if you're in the lab, which 5 from the lecture are in the lab, notes from when we last were meeting are also present in here. But everybody is going, notice how I got sidetracked into Slack, but I'll get this over with. This is the individual that jumped in yesterday from nowhere. I don't know who NMOS MOSFET is. I mean, I know the name attached to it, and I'm like, you already have another account. So I've been warned that people try to hack into workspaces, and that's what Slack calls them. This name up here, DSP.com courses, is the name of the workspace. And if you're new to Slack, it's very easy to use. I like it a lot better than Microsoft Teams because it seems to be leaner. Microsoft Teams tries to do everything, just like Microsoft Word and everything else. It's overbearing at times, but Slack is pretty laid back. I use it on my phone, my iPad, PCs, my MacBook, and so on. And one of the nice things, even though I don't pay anything for this, if we do need to do a conversation, like Brandon is one of my graduate students, we were sharing information, screenshots, and code and other things last night. When we have our weekly meetings, I just simply drop down into here, click that button, and we can be doing an audio call right on the spot. And then once you start an audio call, you can share screens from either direction. You can draw on a whiteboard and things like that. The free version does not allow more than 2 people to be in a conversation at once, so it's not going to work on the channel for the course unless only 2 people are signing in. If 2 of us sign in, like me and 1 of you, and you want to use that for discussing, and a 3rd person tries to join, they won't be able to join just because I'm using the free version. But I can always go to Zoom, and I'm not really too worried about that. I think it's more important, probably in the direct messaging department, that a start of a question in a message will maybe lead to me saying, I'm tired of batting messages back and forth, let's just talk it out. Because talking, I don't know what you guys think, but talking is so much more, it's such a richer experience. It just happens a lot faster, whereas typing is a slower process. But it fits the situation. So I'm going to make a protocol about that, though, and say in a message, just simply say to me, you want to grab one of these, a syllabus, and you can check your name off. I'm going to say as a protocol thing, like I meet with Brandon on Fridays, and then yesterday he started messaging me late last night, but I will generally say I'm about to start the session if I meet with him at a designated time. But if we're messaging and it's convenient for you to do a call, an audio call, just propose that to me. Just don't jump right in, because I might be on my phone, or I might be out walking or running or riding my bike or something. But we can get there, and we can make an arrangement to do that. And I really hope that this will be helpful. I'm not trying to discourage you from ever coming to my office, but these days, this building is still pretty creepy. There aren't that many people in their offices. The staff are really hard to find so far. I'm not going to change that. I'm just going to change jobs. I mean, that's one of the reasons why I'm leaving, though. Plain and simple, I don't like the creepiness around here anymore, and I don't think I need it. COVID is going to fade away, but it's not fading away with a RC time constant that I'm happy with. You know, time constants, right? And electrical engineers, we know all about that. At any rate, that's Slack, and I look forward to seeing you all join in there eventually. So back to the website. I always keep this what's new area or news, and I try to put the proper date on it. If I'm stacking up multiple new messages, the newest will be at the top. I might even put the date or time in here. And this dialogue started a couple of weeks ago when I started writing, this is what's coming, and then yesterday I did more. I mean, as I do more, I kept changing the date, but this is as of this morning, and you can see that it was 7:05 a.m. when I last edited this homepage for the course, because I pushed up a final rework of the intro lecture. You can see that was at 6:53. Course syllabus was yesterday afternoon. And then down in here, I guess, I did this very recently. I put in the problem set number 1, and other stuff in here is still broken because I just didn't take the time to wire it in yet. It's not really ready yet. And if you go down to look at this and say, I'd like to look at the exams early in the semester, well, I haven't done anything there yet. So these are all ripped out of the website. But this will be populated in due time. So it's broken just because I pulled everything out. I don't want to, it's like I have a deck of cards or a hand of cards, and I'm revealing part of my cards, you know, in due time on purpose. So, but I will clean that up. And there's other computer examples with Python, and as I'm heading towards Julia, that's there. Course lectures, this is a pretty useful part for certain people. Like I said, people around the world I know watch these because they write to me about it. But what I will do after today's lecture is this will adjust. I will turn everything on here to red that's old, and then as I get fall 2022 put into this slot, it will be green again, and then fall 2021 will slide over to take the place of fall 2019. I was on sabbatical in fall of 2020, so I don't have any lectures from that time. But you get the idea how that will kind of unfold, and if you need to look at them, you can. I don't really encourage you to go see what I was doing 2 years ago or 3 years ago, because I don't even know. I don't really want to talk about it. It's just whatever happened. But every lecture starts and stops at its own unique time, because it's just what happens during the class. And occasionally they're missing, or we have issues, sometimes have issues with the tablet. I'll lose a video when I get home to go process it so I can post it. I might lose it. And the videos don't necessarily go up right away because I have to compress them. They're taken raw right now as I'm standing here, and then they get compressed down to MP4s. And that takes the software a bit of time. It's not done instantaneously. But you'll know about it because I'll post it up over here. I probably won't start processing this video though until I get home in the afternoon, just because I don't want to take the chance of traveling with this tablet on my bike and having something mess it up where I've got to start it over again. But we'll come back and look at this as needed. There's other things in here about Python. Basics, which is a document I wrote. I don't have something like that for Julia yet, and I'm going to start unfolding and talking about Julia here in a bit. I do have a nice cheat sheet, though, that somebody else created, and I have a link to it, because these are the 3 languages that I care about the most, either in the past or in the present. This is nice because if you know MATLAB only and have never used Python or never used Julia, you can see how the syntaxes stack up next to each other. The reality is, as a student, graduate or undergraduate, working in industry, tools and languages are just omnipresent. You don't do mathematical modeling without using some sort of programming tool. And this is one of the, to me, it's one of the really fun things about working in this area. You're not just writing equations on a sheet of paper and saying, oh well, on to the next one, on to the next one, you know, the homework problem thing that you're used to. You do that, you sketch things out mathematically, but then you quickly jump to modeling something. And if you're working on a project at a company, you're going to be making some prototype, and you're going to try to then do a simulation and then see how that's going to factor into the project you're on. Somebody might give you a data set. It might be classified data. I mean, you name it. It can be waveforms captured from somewhere unknown, and you're trying to discern something. You're maybe trying to make a transmit waveform, or just all kinds of different things that you do. So we have to use tools to do that. I don't know, I'm just curious, does that make you feel good that you know you have to do that, or do you wish that you could just write equations on a sheet of paper for the rest of your life? What do you think? I mean, yeah. Is anybody a little bit nervous about that idea? I'm not taking a survey on paper, so, but if you'd like to make a comment, I'll listen so I can understand if you're a little bit nervous about that. Good? It'll grow on you after a while, though, and you'll say, yeah, I like this. This is what I was hoping for. I started off being a board-level designer for communications electronics, and no, I didn't use LT Spice. It didn't exist at that time. Spice as a simulator existed, but most of my electronic circuit design was done with prototyping circuits and then going to the PCB layout guy in my group and having the board made, and then the board gets fabbed. The board gets assembled by a technician, and then they come to your office and say, here it is. I go to the lab and I start testing it. So nowadays, we don't have to do those steps unless you're in the hardware side of things. You just model everything on the computer and test it there. You might interface to some hardware that's instantiating your DSPs and other things, but it's still a process. And fundamentally, to me at least, over my entire career, and starting in middle school and high school when I was tinkering with electronics, it's the idea that you're making something and you're making something work. I don't know if that inspired you to become an engineer, but it certainly did for me. And I still like making things. It's just how you're going to make things. Are you going to make a PCB? Are you going to write some software that's going to interface to some hardware, so on and so forth? If you enjoy that, I think you're going to enjoy your career in if you go into signal processing. If there's something else that maybe is of greater interest, then that may win out in the long run. But you're here and you're obviously wanting to pursue, what your degree is bringing to the table for employment. And to me it's fascinating. And it might be making something artistic. I play music, I play bass trombone in a number of groups, and making music or playing music is still making something. It's just of a different form. And regardless of what your parents or relatives might say about being right-brained or left-brained, and only certain type of brained people will be engineers and do mathematics and others will do music, I don't necessarily agree with that. I think creativity and the desire to make something happen is something that drives you, and a good number of dimensions in your life makes for an overall sort of a richness, because you're going to leverage one thing to another. So enough of that for right now. I'm now going to switch over to the notes, and I have a newer version of this, so I have to close this down and open up the newest one that I pushed on here a while ago. Okay. So every one of my notes, but I'm not going to be teaching any more classes after this semester, so I can't say I've got covers on all my course notes like I do. But this one in particular, I put a picture on here that represents a signal processing functionality, and we'll go explore that a little bit later, probably in a Pluto notebook for Julia, but you could explore it by other means. But I'm just going to start here and say, if you see this picture and you see a waveform going in the upper left, and then I see inside my block diagram of my system, which has some impulse response h of n and a corresponding frequency response h of e to the j omega. These are the notations of the book, by the way. You don't have to necessarily say, oh, I fully understand that right now, but it is the notations of the book. And then I've got two different sketches inside of the block diagram. One is a frequency response sketch in magnitude of the frequency response in dB, and the other is a pole zero plot. So this is a linear time invariant system, and it's a filter, and this is the configuration of poles and zeros. We'll be studying that too. In the very first chapter of the notes, which is chapter 2 out of the book, we'll be looking at time domain or sequence domain, like the impulse response h of n or a sequence x of n that you see up over here. And then we'll also be looking at in the Fourier domain of taking the Fourier transform of a sequence or the Fourier transform of the impulse response to get the frequency response. Later, when we go to the next chapter in the Z domain, chapter 3, we'll be looking at how we use the Z transform to characterize a system as if it corresponds to a linear time invariant system that has a form that is a difference equation. Then we can have a ratio of polynomials in the Z domain form the system function, and the roots of the polynomials have zeros from the numerator and poles if they're in the denominator. And I know you've seen all these things before, but A lot of the things that you do in this class is just rehashing, but then drilling a little bit deeper than what you did in like 3205 from here at UCCS. It started in 2610, but if you're coming from another school, you had something somewhere. Maybe for some of you graduate students, you almost had this class, or I'll just ask the bold question, did anybody study out of this book before? If you're from another university. It certainly happened to me before. Okay, so that's what's inside the box. And then down at the bottom is the waveform coming out y of n. So sort of a quiz question is seeing what's going in as a sequence of samples looks somewhat disorganized, although you see there's a periodicity in there. But what's coming out as a sequence of samples looks nice and regular after a transient period right over here at the beginning. It looks like what? It's a sinusoid, right? So your intuition should say that the filter is doing something. And if it's a notch filter, which is what it is, which means it passes a bunch of frequencies and then it has the profile of that frequency response, or is like a profile of a thumbtack. That's how I think of it. It's like if you hold up a thumbtack, you would see it's flat across the top and has a point coming down, or maybe a nail head, I don't know. But that's sort of the shape of the frequency response magnitude. So that thumbtack is tacking down the frequency response to be 0, or in dB minus infinity, and that's what happens in the z-plane there, and we'll learn about that. When we sweep in the z-plane around on the unit circle, which is this circle, at different angles, that corresponds to omega. So omega equals 0 degrees, and the e to the j omega is right here, pi is up there. So that 0 is somewhere just less than pi, or I mean pi over 2, less than pi over 2, or about 80 degrees or something like that. So that's a notching frequency, and then the pole that sits behind it is controlling the sharpness of the notch. And if you see just the transfer function as being a single notch like this and flat everywhere else, there's another assumption you can draw out of this, or another fact you can draw out of this is it must be, well, if we get a single sinusoid coming out, what must the input be composed of then? If you're a detective, a signals detective. 2 sinusoids, right? Because if it was more than 2, then that single notch would not allow us to get just a single sinusoid out. Does that make sense? And this is not really complicated in the end, but you know, when you first start on something, your brain is like, where am I? I'm in outer space. I'm cruising around. I'm trying to zoom in to where I need to be to get into this topic. So I'm just making you start to think about stuff. It's pretty cool all the way it works. So, and the fact that there's a transient over here, is that surprising? I think in circuits you're trained so much to think sinusoidal steady state. You study transient analysis when you first study circuits, and you, at least for me, I enjoyed transient responses, but sinusoidal steady state response was so much easier to calculate. It was just a simple analysis with phasors or complex arithmetic, whereas the transient response, you had to learn more about differential equations and particular solutions, forced responses. We'll be doing that stuff in here, by the way, but once the transient's over with, you're like sailing smooth and easy. Applications, though, in signal processing don't necessarily not care about the transient. As a matter of fact, when I do a demo a little bit later on this problem, you'll see if I make the notch narrower and narrower, in other words, to make it be really pinpointish, as if it's only going to excise one signal. Think of that now as being a jamming signal, and you want to have your wideband signal come through and only have a small little excision where the jammer sits. A problem that will occur is when you make this really narrow, you're going to have a time constant that's very large that corresponds to how long it takes for the transient to die away. So if things were moving around rapidly, then too much settling time would be not good either, because you'd be just agitated that my system never settles, the jammer moves to a new frequency, and I'm trying to adapt. But adaptive filters in DSP can be used to do this as well. So now I'm just going to, I guess I should make this bigger. I'm going to move on from there. I'll come back and look at a simulation of that a little bit later. I'm going to try to move quickly through this stuff. I've been using this basic setup for many, many years. I've made a few minor changes again this semester, but I'm not going to do a radical shift at this point in my career. So DSP, the term Modern DSP was a course title that was here in 1984 when I started teaching here. You can say, wow, that's a really long time ago. So I didn't create the name. I mentioned it to somebody in my family, and they said, if you were teaching it way back then, how can you still call it Modern DSP? They were laughing, like, this can't be true. And of course, you know, I'm teaching out of the third iteration of this book by Oppenheim and Schaefer, who are, you know, older than me, so they're retired, or at least Schaefer is definitely retired. Oppenheim is at MIT. He might still be hanging around there, I don't know, but each iteration of the book did remove some older material and put some new, more contemporary things in. So I'm pretty much believing that we're pretty close to being, the word modern is not a bad name, but I'm not sure who created that when they said that. It's like, would you not want to study the most modern thing? For some subjects, if you're taking a history course, yeah, you definitely don't want to study the modern stuff because that's not the historical part. At any rate, though, contemporary DSP maybe is a better name. So it's composed of theory, the current technology that we can bring to bear to use the theory to develop some solution for an application, and then, of course, the applications themselves. See if my pen will work. I'm going to guess the battery needs to be replaced on it. So I'm going to draw with my style or with my mouse. The major focus of this class is on theory, working with the mathematics, but you're going to get plenty of opportunity to explore certain types of solutions and then some actual application examples that will come with projects and problems. The actual technology, we'll be using new software technologies which keep rolling forward for sure. And I'm going to take the microphone off here for a second. If you're taking the lab, and there's still seats available in the lab, you will be using this microcontroller. Just pass this around. To write real-time DSP code in the analog world through a codec, audio codec, an A to D and a D to A. And then do interactive programming. So that's kind of exciting. This is representative of something that's very low cost, just using a microcontroller. That board costs $50. It just so happens it's now extinct. It's no longer made. As of about a year ago, they stopped making it. It was made by Cypress originally. Cypress was acquired by Infineon. Cypress has an office here in Colorado Springs also, but they dropped that from their product line, which is normal. Our semiconductor devices in existence for that long. Something new comes along and the old stuff sort of gets cast away. I have a bunch of copies of the board that I got from a contact at Infineon, And that's how we're going to keep the class going. I'll say more about that when I appear in the lab session later this morning. But there's 5 of you that are in there. There's space for 10 easily. I have boards enough too. So it's just something to think about if you're interested in that. Come to that. That meets at 10:50. Is that right, Jack? Because you, I know, are in it.
I was zoned out. I have no idea.
I think it's at 10:50. It's like shortly after this class is over with. Okay, course perspective. I'm going to talk about background and where do we go from here, and then what the course is about. And I'll spend some time on computer modeling, analysis, and simulation tools, talk a little bit about projects, and at the very end, my instructor policies. I'm going to skim over a lot of this because I find myself just not needing to spend the time on it, but I just want to say a little bit about our textbook. Oppenheim and Schaefer were some of the first people to write a digital signal processing textbook as it was moving from the theory and graduate research side into practical application for undergraduates. So this book is a ways down the road from that original book. And that original book was called Digital Signal Processing, but then that led to this book. The IEEE is very connected with signal processing. So we have the IEEE Journal on Signal Processing, and we have the annual conference, Acoustic Speech and Signal Processing, ICASSP, which not recently, but years ago I went to a few times with papers, and there's always been a trade show with that. So those are fun things to do. If you're a graduate student, those are the types of things you would typically do. But if you're anybody that wants to develop something for work or whatever, you rely on papers that have been published to learn about things that people have done. I mean, I'm involved in my work at Augustus Aerospace right now with trying to develop something that they need help with some algorithms. They need to know how to do this for a project. They need to deliver it immediately, of course. I mean, actually, they needed to deliver it back in May, and they're throwing me at it right now to help. So they're also throwing me a bunch of papers to read, and I will read a few papers. I'll probably look at some more that I'm finding as references to the ones they're thinking I'm going to find what I'm looking for, and then it's going to turn into code, and then it's going to go to the customer. This project is commercial, so it's actually something that's going to help characterize the public radio system in the state of Colorado. It's a network that we don't even know about, but it's called P25. It's a standard, and it's used around the country, but I guess here in Colorado they want to do some more characterization of certain types of link scenarios that arise in the network. What are the error probabilities going to be? So they're building a test set that can work with a software-defined radio that will just capture signal samples and then post-process it later. So that's where we come in. That's where I do almost everything involves complex signal samples from a radio. Complex just means the sample X event I was mentioning earlier is now the real part plus the imaginary part. So it's called in-phase and quadrature usually. So IQ samples is what we deal with a lot. So that this project, what's cool about it is the primary developer on it is not a communication signal processing guy, and he's been making pretty good progress just with common sense, but he's a very good embedded systems developer, and he writes C and C++ code. So it can run on a laptop, though. It doesn't have to run on special hardware. The capture SDR will get the IQ samples into a file. Usually it's a binary file, and then the software can just run on the laptop. It's been built up from C++, and then it'll produce the outputs. It'll take as inputs the frames of IQ samples. And that's the kind of stuff I've been doing since I was on my sabbatical in 2012 2020 to 2021. I'm doing more of that again. So I'm doing a lot of C++ coding using object-oriented techniques, but I'm prototyping, and I'm also trying to leverage the power of Julia, which I'm going to still talk about. I'm just throwing that name out there because you're going to understand why I'm excited about it in a little bit here. Technology, we have integer and fixed point, which is common in cell phones still to this day. Floating point implementations are much easier to code for. The board I passed around has a floating point unit on it, so you can program in floating point, and you can program in fixed point if you want to as well. Usually a float, though, is a 32-bit, 16-bit float, so it's float in C. Well, no, excuse me, it is float 32. I'm getting myself confused. Integers are generally int 16s, so if you're taking the lab class in lab 3, you'll start working with the board, and you'll have to get yourself reacquainted with things from the C language, which is also C++, the data types that you work with, like float 32, int 16, which is signed 16-bit integer, and you have to pay attention to all those things. But our languages like Python and Julia, we can model it all at that level if we want to. So we have that full bit true characteristics that we're interested in when it has to go run on some hardware somewhere. FPGA is at the bottom because FPGA is whatever you want to make it. It's variable precision bit widths and things of that nature. I worked with that for a while on my sabbatical too. And it's moving towards more C++ to write FPGA fabric code. I'm kind of excited about that because that's stuff that they let me spend over half a year on, trying to make headway on programming without learning Verilog or VHDL. All of you know Verilog, so you'd be able to cash in on that, but rapid prototyping is something that everybody wants an FPGA to do at some point. It's not easy, though. The rest of this is a bunch of applications. I'm not really going to talk about any of them. You can just look at them. I think nowadays it's so pervasive that it's just, you think DSP must be in there, but maybe you don't think that way. Maybe you don't think, I have this gadget. I don't care to figure out what's inside of it. But you're an engineer, so you should be saying, I do want to know what's inside of it because that might be my next project. I will say at the end, though, the last topic was military and aerospace. This is where DSP started making its inroads into our technology base for our society. No surprise there, right? Where do we put a lot of our heavyweight technologies in the military? Because we're in the arms race with the world. I mean, that's just a fact of life. That's the way it's been through all history, that you have to stay going in that fashion because that's how things function. I mean, you might have a different philosophical view, but I'm not going to go down that path right now, but that's just how things function, at least in the United States and other countries. We're on a slope, a technology slope, and if you stand at one spot in that slope and don't advance, you're actually going to get overcome by your opponents, so you have to keep doing that. And of course, as consumers, we enjoy that because, you know, consumer applications that we have today were started with military programs typically, or space programs or something. I already mentioned this, software-defined radio is a really big thing. So I did not rotate this yet, but I am going to rotate it. If I can remember how I rotate.
Click the check.
Yeah, okay. That's too obvious. So I created this one, I reworked this one last week or the week before because Some of you had Dr. Semiari for a course maybe last year or the year before. He up and resigned in June. Very, very disappointing to me because I was looking to hand things off to him, but he just beat me to the punch. I'm a little bit jealous of the fact that he can just get up and walk away, and now after I leave, there's nobody. A committee has been formed though, and I modified this document just so I could share it with them because the department chair doesn't really understand how everything I've been teaching has factored into all this stuff over the years. It's not quite as simple as he's trying to make it, so I wanted the committee to understand what's been going on, and this was always my slide to say, how does this course fit in? And you know, this is where we are right here in this course perspective. We have signals and systems courses you take as an undergraduate, which plug into this. You take prop and stats, which plugs into this in a small way because we will use that for some modeling. And we also have, if you're taking this class as a senior elective, the ability to go take the 1-credit signal processing lab. But in reality, you can take the 1-credit signal processing lab just from 2610. You'd have enough background to be successful in that. This helps, but that's sitting out there. And these are all the other courses that I've been involved with. I haven't taught everyone that's on here, but if I would be staying, for example, I would move down to teach real-time DSP in the spring. Kaylee had the class last spring. I think it was a good class for you, right?
Yeah, it was.
I would possibly be teaching this class. It's actually been an odd year, so it would have been taught this spring in 2023, Statistical Signal Processing, which is ECE 5615. Some graduate students might have moved on to that, and then of course Comm Systems 1 is in the spring. I think the professor for that class or instructor is going to be a PhD engineer from Emergent Technologies. I interviewed there last spring, and one of their engineers said, hey, if you're leaving the university, I'd like to start being an adjunct. So in June, after the luncheon for Dr. Semiari, Dr. Kalker's just like, I don't know what to do, I don't know where to find anybody. And I said, no worries, I have at least one person that wants to help out. So Comm 1 will be taught. I'm also working with a former graduate student who's doing the signal processing lab. I'm handing it over to him, trying to get him indoctrinated into the processes. I'm going to try to move on to try to get him involved with the Comm Lab for the spring. So if you're planning on taking those courses next semester, I can tell you right now that these two will definitely be offered. And right now, the satellite communications class that Dr. Semiari had developed in cooperation with Kratos, or getting inputs from Kratos, is being taught right now as far as I know. Is anybody taking it? And the instructor is somebody from Emergent. It's the same guy. Have you met yet?
I have not.
Okay.
Mark Frank.
Mark Frank. I need to start talking with him because I was hoping to hand off to Dr. Semiari. He's really the only person that I can hand anything off to. So, he knows that we have to talk. I wrote him an email in the summer. It's kind of traumatic. These things do happen. When I started here in 1984, I took an office over in Dwyer Hall that had been vacated by a professor that was teaching signal processing and microwave electromagnetics. I interviewed a few months before that. I never got to meet that man when I interviewed, and when I showed up for my first day to move into my office, he had already departed to go to California to teach at Caltech or something. So I never met him. I never got any handoff. I never got any indoctrination on anything. Course-wise, I started from scratch. So I'm just saying that it can be done. It's not maybe the nicest way, but survival will occur, and hopefully it will keep going. I wish I could say more, but that's about all I can say because I'm not going to work for free. I have other things to do, and you can probably understand that. Do you have any questions about this, though? These courses with the question marks are the ones that we don't know for sure. Mark Frank is doing this right now. These are other courses. If I'm sounding like I'm whining, I'll just say a little bit more. We had Dr. Semiari for 3 years. Before that, we had Professor Harrison, who ended up going to Brigham Young. And then before that, we had Jennifer Price. Each of those 3 faculty members came and lasted for 3 years before they went somewhere else. I invested time in them, trying to get them brought up to be my junior to me, and then all 3 of them left. So I feel, in the words of baseball, like I've struck out now. But I don't think that responsibility was mine anyway. I mean, it was their life, and they got to decide what to do. But am I disappointed? Yes. You're going to be seeing this in your work too. People do change jobs. And I guess the newest thing is called quiet quitting. Has anybody heard about quiet quitting? You've heard about it. You probably know what it really is, but it sounds like something that it's not. It's not quitting your job. Quiet quitting is just a way of saying, hey, I'm only going to do so much, and that's all I'm going to do.
It's doing literally exactly what's in your job description. So if you work like 9 to 5, you quietly get up and leave at 5.
Yeah. But engineers, that doesn't exactly fit our mold. We don't work 9 to 5. We work, I don't want to scare you about this, but projects tend to ebb and flow. So maybe you have an easier day, but then there'll come a time when you're testing and you might have to go out into the field to test, and you're working like maybe 12 plus hours a day. Or at least I did things like that. I get to go on a field trip to White Sands Missile Range to test a laser comm system. So there's pros and cons to it, but I've read both sides to it, what it means. But it sounds like you probably read both sides to it too. It's like to make sure you don't get destroyed by your job or get overworked or taken away. But I was kind of shocked when I read about it, because I first thought it was something that it isn't. But it's apparently a new language thing that's out there. So we're going to focus on one-dimensional signal processing in this class. Nuts and bolts of the 1D side of things. We could have 2D, which would be image processing. 3D would be 3D signal processing, which that's pretty popular right now too. If you think about point clouds and LiDAR and what's the other term that I got involved with a bit on a project. What's that name? It's where you can take a bunch of images with your camera, like walk around an object, and then you process it into a 3D image. It's called photogrammetry. Has anybody ever heard of photogrammetry? Point clouds, LiDAR, things like that. Have you heard of that? It's something where you can, basically a point cloud is you get all these points from these different images in the case of the photogrammetry, and then you get similar points in space when you look around at different angles, and then you can reconstruct a 3D rendering from that. So I was using it looking at it with a graduate student who finally finished this summer for modeling ahead for acoustics and modeling in particular around the ears, which are called the pinna. The shape of this controls how the sound is processed by our brains. And what we wanted to do with human subject modeling before COVID started was to do, using photogrammetry, get 3D head renderings for individuals, and then do acoustical wave modeling in a product called COMSOL Multiphysics to actually get the acoustic properties of in the time and frequency domain. It's called the head-related transfer function, which gives you the frequency response in each of your ears for acoustical plane waves arriving at all angles in space. And then you can better understand how, the features, your shoulders, your head shape, your ears, and everything control that frequency response, and then be able to understand how you might help somebody that has a hearing impairment. Or I was also interested and did some work in audio virtual reality, where you can put on some headphones and you can synthesize sound coming from any direction if you have this HRTF, the head-related transfer function. So, I mean, I have a simulator for that in Python right now that I can put headphones on you and use an approximate HRTF, and I can send sound at you from different directions, use slider controls, and spin things around, and it's pretty cool. Some of you are probably interested in virtual reality for the video part, but this adds the other component, the audio side of things. I'm getting sidetracked right now, but one of the things I visualized, and maybe it will still happen, maybe not, is you would go to a theater, you would have your HRTF on your flash drive, you could plug it into the seat, and then you would put headphones on, and then everything would be rendered very precisely for what's going on in the movie or something. Does that sound pretty far-fetched? Because video games that some of you play have some of those effects already present, right? Who plays a game that uses some HRTF assumptions to get you audio and action coming from different directions? They're out there, right? I know that they have an approximate HRTFs, but if you had your own, that would be your own custom footprint or fingerprint to control that rendering. But we're also interested in other examples in that, where you might be in a conversation and you might have on your cell phone like a joystick on your screen where you can focus the audio to only pick out one person in the crowd. That's called the cocktail party problem, where it gets louder and louder and you're trying to carry on a conversation, the two of you, and everybody else is throwing up so much interference you wish you could just sort of zoom in on that head. I think that's coming too. I mean, that's pretty exciting. You get right down to it. Maybe it's not, maybe it doesn't sound exciting to you, but I like it. It's pretty interesting. Okay, sorry I got sidetracked. These are things though that I have dreamt about and was on a proposal with the NIH, but apparently we didn't get funded. It was with a local company for some noise canceling things for a hearing aid device to help people that are hearing impaired and hear better by being able to cancel background noises that are annoying, like cars and other foreign sounds that just make it hard to hold your cell phone up to your ear when you're standing outside near traffic. Nobody's ever had that happen though, right? I mean, I'm saying that facetiously because you can just do that and that'll help, plug one ear, but that's a very nice application that I think it's making progress, but making that happen more and more with deep learning neural networks and other things can help with that. So I'm listing the primary background for this class would be 2610 and 3205, which are the Signals and Systems undergraduate courses here at UCCS or equivalent. But the math here is going to be taken further, and we'll also spend a lot more time on A to D and D to A modeling, and a really big topic that doesn't get covered at the undergraduate course level would be multi-rate processing. The idea that we're going to sample at different rates within the system. We don't just say we're going to sample at a really high rate because we need to be efficient in our sampling rates for the engines we have running our system. So we'll study mathematically the multi-rate side of things. And we'll also look at quantization effects and look at some interesting properties of systems, one of which we'll go through and you might say, oh, that's kind of cool. Minimum phase, maximum phase systems, linear phase systems, what are nice things about them and what are characteristics of them. So there's a chapter in the book, chapter 5, where we get into some properties of discrete time systems, such as minimum phase, maximum phase, and linear phase. And they're part of things that we have to do. I mean, one example where minimum phase and non-minimum phase thwarts us is in cellular telephony, when you have multipath present, you have a channel model then, and you can model it as in the discrete time domain. So I'm getting my signal at my cell phone maybe directly from the tower, but I'm also, or maybe I'm getting it reflected off one building or another building, and the distances that those rays have to travel of microwaves are going to be different, and the intensities are going to be different. So if the more distant signal is stronger than the closer signal just because of some attenuation properties, then we create a non-minimum phase system, and then that creates a behavior that's harder to equalize or compensate for. So that's where some of those ideas come into play: equalization, equalization and fixing multipath issues. 5G goes after this in different ways, though, but it has some amazing signal processing things in it too. I got to work for a company on the side over the past year until the project went away. Have no needs to know. I don't know who the customer was, but I learned a lot. 5G has 8 antenna beams will come down, and they'll be able to do spatial signal processing with antenna beams for cellular networks. We don't really have that yet. Notice on your phone, it doesn't say 5G, it says 5G something else, right? Is it E or, I don't know. It's not really here yet, though. The true 5G capability with the multi-element antennas is not really working here in Colorado Springs. I'm not sure where it's even working. I mean, it's working in bigger cities, but that's some really nice stuff, too. Introduce random, discrete time random signals so we can model quantization of waveforms and quantization noise, and then also be able to look at quantization effects in the implementation of digital filters and things. So a fun area for me that I really enjoy because I like making things. I've said that before, I'm going to say it again. I like making things, and nowadays it's in software, is what tools do we have available? So for the longest time, I used MATLAB, starting in about 1986, let's say, is when MATLAB first came on the scene. MATLAB stands for Matrix Laboratory. It kind of took me away from using C and C++ to having a platform that could allow visualization, and if you could vectorize your code, you could get it to run quickly. I also started working with Mathematica about the same time. It's very good for symbolics, and it's less good for numerical type stuff. The language does everything, and it's still out there, but I don't really, unless you used it before, I'm saying it's probably not a good choice for this class. Does anybody use Mathematica? You've heard of it though, right? You might have seen it in high school or something. But when I was on my sabbatical working at Emergent Technologies in, I guess, around 2012 or so, I started exposing myself to Python because they wouldn't buy me a seat of MATLAB. It's very expensive. And I used Octave, which is an open source MATLAB, but it's not very fast. And I didn't make very good graphics. So I decided to start exploring Python, and that was how I got started with Python. But then I wrote the book Signals and Systems for Dummies, which you saw my advertisement for that over here. I wrote this book in 2013, or published in 2013. I started it in the summer of 2012, and it's not really a very big seller. I didn't even bring a copy of it down here. I think it's good if you have to refresh yourself on discrete and continuous time signals and systems, but the important thing for me was I told my editor that I wanted to provide some software tools, and I wanted to use a free and open source language, so I didn't want anybody around the world to try to bootleg MATLAB. I don't believe in copyright infringement like that on tools, so that's what for me. That was the big thing that I pulled off in the book. Was I was able to start developing the package for the book itself, which is now the package is called Scikit DSP.com, and it is on GitHub, and it's downloadable from the Python community, and you're going to be putting it on your computers if you haven't already. So I expanded it considerably from where it started. There's a module within Scikit DSP.com called SigSys, which was the original chapter that I wrote, or the original module that I wrote for the book. But it's been tweaked here and there throughout that time. And Scikit DSP.com sits on top of what's called the SciPy stack, which is composed of SciPy, which has a module called Signal, which is the signal processing module of the SciPy package. And then, I'm not going to be able to be very good at writing this out here, but NumPy is the foundation of everything pretty much in Python for scientific computing. Python is a language that is very broad-based. It's kind of like it's a Swiss Army knife. It can do anything and everything. It can do hardware, it can do database stuff, it can do websites. I mean, there's just all kinds of packages in the Python community. And it was started by a guy in England. It's sort of a side thing he decided to do one afternoon or something. I mean, he named it after Monty Python's Flying Circus. It's not, has nothing to do with a snake, although that's a symbol. A snake appears, a python appears a lot in literature and in books and things, but it was Monty Python's and the Flying Circus, which is a comedy thing, very dry humor, British style. I might wear a shirt that has something from about the heavily laden swallow. Does anybody know that story? So the SciPy conference I went to that year, they made a very mathematical looking thing about how they optimized the energy and the capabilities of the swallow so that it could fly with its eggs or whatever is in the movie. I mean, it comes from that movie. It's kind of really crazy stuff, but a PhD student came along in the early 2000s and for his dissertation wrote the first NumPy package. So that endowed Python with vectorization capabilities and gave essentially a whole library of things were written in C++ that you could directly couple into without having to be interpreted with everything that you do. So NumPy brings to the table the idea of the ND array, n-dimensional array, and all of the vector operations you can do with that. So the ND array is the key to Python's efficiency and speed in numerical stuff. Python comes with a structure known as a list, and everything in Python is an object because it's object-oriented all the way through, but lists are not very fast. And if you start learning Python or read the basics that I wrote, if you're a good place to look if you want to learn a little bit about Python would be Python Basics, which was written in a Jupyter notebook, and it's available on the website here too, but it goes down and just talks about the very first thing that I have in the book is called, or in this document, is called Before NumPy, just learning the basics of the Python language and how you would do things. And then when you bring on NumPy, it's very similar to MATLAB at that point. Julia, the language I'm going to start talking about here pretty soon, does that even more, and it does it faster. So that's the really exciting thing about that language. But I had a student when I first was teaching with Python over 10 years ago, because I've been doing it now for over 10 years, and nobody's died from having to learn it yet or anything like that. he never got the idea of using the ND array, and he used a list for everything. He kept it really simple, but he had really slow code, and I was just confounded by why he didn't want to use the ND array. I mean, hopefully nobody will do something silly like that, because vectorizing languages that are interpreted is what you have to do to get speed and efficiency. If you're writing in C or C++, you write a for loop and it compiles with the optimizer and is really, really fast. Now, I'll say a little bit, Julia takes that further though. It compiles everything down to machine code using C in the background. It takes a little bit longer to make your first function call, but once it does that, it's cached, that compiled version, and it runs at top speed all the time. So it kind of, you don't have to think the same way when you work with Julia. And I'll be saying more about this, but I'll just say right now, people are saying in the community that it solves the two-language problem. Does anybody know what the two-language problem is? I'm not a computer scientist, but I'll just tell you, you're going to have to get into this, because this is the way of being an engineer in signals and systems. You are engaged with the software communities a lot, because it's how we make things. So the two-language problem is you have something like MATLAB or Python, let's say, or Octave, which is really slow, to prototype and make quick and simple models, quick and really fast, rapid prototyping. But when you start cranking them, pushing them harder to work with real data sets that might be very large, or try to stream something through it, you end up having problems because it's not that fast. So then you have to go to a second language like C or C++ to recode your prototype and then get it to run faster. Or maybe that's how it gets instantiated into the actual hardware or the final product or application you ship to the government or customer. So Julia, because it compiles everything and runs much faster from the very beginning, they're saying that it solves the two-language problem, and that you can write once and you can use it and push it really hard, because it will run 10 to 100 times faster. And I've noticed that in some things. Obviously, the proponents of it, and it was developed by some people at MIT probably about 10 years ago, say it solves every problem, but everybody says anything that's new solves everything, right? We're all used to marketing pitches, so I take things with a grain of salt, but I am very impressed by the speed though. And there's software-defined radio interfaces people have been writing and contributing to the community that talk to some of the SDRs that I have, and I'm still evaluating that, because inevitably when you're using hardware interfaces to a language like MATLAB, Python, or Julia, you have snags in getting these drivers to work properly so that you can talk to your hardware devices. But I'm hopeful just the same. Where it's going to go, I don't know exactly. But one thing I know for sure, it's going to change over your lifetime. It's not going to, things are not going to stand still. What we have right now is going to migrate in some direction. Does everybody believe me on that? It's just going to happen. And what happens if you don't follow along? Where are you going to be? And this is not a question of quiet quitting. It's a question of maybe you're not working anymore because you're not staying with the changes. Things do change in electrical engineering. They change pretty rapidly. Even in Colorado Springs utilities, where you do power systems, we do change technologies there too. I mean, you might think, well, does things have to change in getting the generator through the power transmission lines into our homes? There are still subtle changes that are made, but some things are more rapidly changing than others. I'll acknowledge that fact. If you're a mechanical engineer and you're designing tools, making a box wrench, everybody know what a box wrench is? It's like your basic wrench that has a rectangle to put on a bolt on one side, and then it has a complete box on the other side to go over the bolt. Does that seem pretty mundane or not? I'm just curious, because you're not mechanical engineers. I took a lot of ME courses when I was an undergraduate, but the basic designs there I don't think change very much, but the materials might change, something that makes it stronger and more durable. The worst thing that can happen on a tool that you're working at beyond its capacity is it shatters and sends metal flying at you and wipes out part of your body. Nobody thinks about that though, right? You work something and then it breaks and you hope you don't get hurt, but that's another thing about engineering. We have a huge responsibility to the constituents, the users of our products. So I got into that a little bit with Julia, so I have that two-language problem thing in here. Where I'm at right now, though, and where the company's at, and where most companies are at, C++ seems to be the center of a lot of that work. For developing real-time in the lab, we'll just use a development tool, Kyle, for the Cortex-M series. That's a product that you get introduced to here at UCCS in your undergraduate course on microcontrollers. And for the time being, Verilog and VHDL are still the mainstay for hardware description, but Xilinx is working really hard with its Vitis IDE and the ability to write kernels in C++. That's what I learned about for over half a year in my job at Augustus Aerospace, and it works. But there's still issues with getting everything to play together, getting certain libraries to play together, being able to build things using IP, and then you instantiate it, and then you get to talk to it from, say, an ARM core will talk to a kernel that's running in the Xilinx fabric, and then you can talk to it. I was talking to it using a language called OpenGL, which is, or OpenCL, I mean. OpenCL, not GL. G is the graphics language. OpenCL. But then you still have the issues of the bottlenecking of getting signals in and out of the fabric. The fabric code runs really fast because it's instantiated in FPGA, and then you have your ARM core that's running some C++, and then you push data in, take data out really fast. There's just challenges, but these things are going to be changing. I know they're going to change, and it's going to just keep moving. It's not going to go quantum leap. It's just going to gradually move along, and pretty soon it'll be more mainstay, is what I think. I got one of these donated, a Kriya SOM system on a module, and it programs with the Vitis Unified Software Platform. Maybe that will be the successor to what I do in the DSP lab. I say I do because I may spend some time with the donation this semester and get the student, or the former student, Chirant Sidiapa, involved with that because he knows VHDL and Verilog. I don't know though. Microcontrollers are cheap. Kriya SOM is $199 and 6 or more months lead time right now. You know, technology is so hard to get right now, but I'll maybe bring it in here. I didn't put it in my backpack, but. So now it's time for a break. The doors are slamming. That means people are leaving. We're not leaving though, we're coming back again. So how would it be if we come back at 9:30? And then we'll start with the icebreaker at 9:30. Does that sound good? So I'm just going to suspend my video, and then you'll come back in here and we'll carry on. I won't start up the video till the icebreaker is over with. If you're new to the campus, talk to somebody in here and follow them if they're getting coffee, going down to what used to be the sanatorium grounds, and now it changed its name, right? The coffee stand down there in the student center. Or if you just drink water, like I do, do that, walk around the hallway. If you want to talk to me, that's fine too. So just getting back to the video now. We just got finished doing the icebreaker. Hopefully that sharing has helped you understand where each of you are coming from and where you're going to. I want you to get as much out of this as possible. Unfortunately, I can't make you all hard driving signal processing for the rest of your life type people, but some of you are going to do it. Some of you are going to spin off into different directions, and exposures that you get in here are going to be important. In some senses, I wish I didn't have to teach you to do the mathematics, but learning how to work mathematical modeling into everything is just a skill unto itself, whether it's a DSP problem or an electromagnetics problem. Just being able to tackle that and start breaking it down is fundamental, I think, in everything you do as an engineer, and knowing how to bring modeling in to assist you. Because as I was saying during the break time, one of the things that you can do almost always in this course, if you're given a math theory problem from the book, you can scribble it down, you can start working on the solution that I want you to get, and I want it math on the page or math on paper. But then you can build a model up and you can attempt to see, is this making sense? And you can try to simulate that or model it and see, is this what's going to happen? And if you're like me, I won't try to solve the problem always to total completion on paper, because I might get stuck. I might say, I don't know, I can't quite conceive of how to approach this or where it's going to go. So I'll jump over onto the computer and start making a model. And then I'll make some headway and I'll maybe see some numbers coming out, but it's like, are these believable? Is this reasonable? So then I jump back to the math and I start getting it further further along. I have to go get my water. My throat's starting to give out. And then I kind of start working iteratively between the two. And so in the end, I will have an analytical model on paper that explains the behavior and the nuances. And then I will be able to do certain special cases on the computer and say, look, it matches perfectly. And then go a little bit further. And this I'll do in the solutions I provide to the homeworks and things. I'll see, oh, there's another way to solve this analytically. And you see one angle on it, but if you look around for another slice into solving the problem, you'll say, oh, I could approach it like that, and that might even be easier. So I oftentimes will encourage you to take more than one approach to a problem, because maybe that will work better for you. In the beginning, though, you're probably happiest if you can just solve the problem, right? You don't care how, you just want to do it. But I encourage you to kind of see if you can angle in from a different direction, because that way you expand your horizon. Okay, so computer projects do factor in, and I want you to be able to do that, whether or not we use Julia. I have to get a new battery for my pen, or Python. I'm going to try to bring you up to speed on that as we move along. It's going to be one of the two, though. I don't want you to stick with using MATLAB. I want you to explore the open source tools that are out there, because that is what a lot of companies are now using. I'll just put Kaylee on the spot. Working at Emergent, are they using MATLAB for anything anymore?
Only one, more theory guide actually using it.
It's still using it? Okay.
Python and C++.
Okay. So I didn't lie to you when I said that was the case. I mean, that's exactly what I'm doing at this other company. And Julia is not really hitting the scene yet, but it will, I think. I say I think because I can be proven wrong. I mean, what do I know? I just read a lot of stuff and I follow a lot of articles. I attend the free Julia conferences that are held in the summer now. Things are moving, though, that's for certain. Whether Julia drops down and comes back up as something else. But Python is very stable, so So the projects familiarize you with things. One of the first project that you'll do will familiarize you with modeling, and whether you want to do it in Python or Julia will be, I'm going to leave that up to you, but I'm going to try to put in front of you a lot of different Julia results too. And the cool thing is we're going to be using Jupyter Notebook. And Jupyter Notebook, if you look at the spelling there, look at the spelling of Jupiter. Does it look like it's misspelled? What do you think? I mean, you don't think about the planet Jupiter very often, but that's not the spelling of the planet Jupiter. There's an I in it, right? It's an I, not a Y. Is that right? So it's not a misspelling, and the reason why is when Jupyter Notebook was created by Python developers, it's an environment that works in a web browser, and we can look at it right here. It looks something like this. This is a Jupyter Notebook, and a lot of cool things you can do with it. Jupyter, though, JU stands for Julia, and PY stands for Python, and TER, I don't remember what that stood for when they first created it, but Jupyter was to say a work environment, an IDE for developing code that has text, graphics, and code and mathematical equations typeset as a document that can be shared and used as a training tool. It was originally created to host multiple languages. So I can take a Jupyter Notebook, and this is what I want you to get up and running, and I can do Julia in it, I can do Python in it, I can do Octave in it, which is free MATLAB. You can do MATLAB in it. I have a PhD student in Omaha who's running MATLAB in a Jupyter Notebook too, and other languages. So I don't know if that excites you at all or not, but the notebook is a portable document that can be shared, and it houses more than just a script that you run the script and you get a bunch of plots. MATLAB kind of was built on that concept, but having the notebook lets you have text, put math equations in it, explaining what you've done, why you're doing it. You can have a code cell then that does something, and then you can have graphics output. And if a few months later somebody at work says, hey, what did you do here? How does this work? Oh, I have a Jupyter Notebook all ready to go, and what did I do? Oh, I can run these code cells, and I can read my text and my notes, and I can quickly ramp myself back up again. Whereas if all I have is a chunk of code, I look at it and I say, I run it and it produces some plots, but I don't have a lot of documentation with it. I'd have to have written separate documentation. So to me, Jupyter Notebooks are nice because I can document things as I go, and I can get back to it again. And what I use in this class a lot is Jupyter Notebook examples or templates that I can hand you and leave things out of it and say, here's a starting point. You can finish it. You can add more to it. So you have something to bootstrap your learning process. Does that sound nice? Or, I mean, I think it's nice, but I'm biased. The problem is you have to set up the tools. You can't just go install MATLAB and have it all there. You have to get these open source tools installed. But I'll just segue off for a second to say what have I done in the course in that regard. Get back out of where I was. So the process I'm taking on for this semester is one of two. The old approach, which I don't really want you to use, but it is sitting up here. It says document from spring 2022. This was an approach I was taking to get Python up, and it also to run Python in the Modern DSP lab. This will work, and if you followed this last spring with me, which 3 of you were in that lab. This will still work. It won't get you Julia. You'll have to do that on its own, but Julia is not that hard to do. I downloaded it, and if I was to go into my downloads, it's just sitting right here. I just have to unpack it and install it on this machine. It's actually already running on this machine, but it's actually running right in a terminal right over here. It's running in this window. I launched it from right here. Way up here, after I ran a bunch of commands, I typed Julia at a terminal window. So that's another thing. Terminal windows are your friend. They're not your enemy. You're into the nuts and bolts, but this is what we do. We don't have a glitzy GUI at the start. We use terminals a lot, and you'll see why, because it cuts to the chase faster rather than having to learn Microsoft Word. You want to learn, I mean, you know Word, but you want to learn a big fat GUI every time. You want leaner and meaner things can get you into it. But I've got stuff launched here. This other PowerShell window is where I launched after I did some updates to my system here. These are all the updates, but I did launch way down in here. I did type at the terminal window Jupyter Lab, and it brought up Jupyter Lab for me. So I use the terminal a lot to launch things. But at any rate, what I wrote last night was this document: install Jupyter and Python together, and also get Jupyter Lab all wrapped up. So this is what I want you to study. You can do Python from within the Julia language. So this is what I want you to contemplate. If you follow this document, though, and it's talked about in the syllabus, you will have Jupyter Lab in the end, and when you get all the way down here to the bottom, you'll have along the way, you'll get another type of notebook called Pluto if you want to try that. But when you get down to the very end, you will be able to launch up an environment for Julia, and then you'll launch up iJulia, which is a package. And once iJulia is launched, you will, at the Julia prompt, and it's IDE that you run there from the terminal, you will say import iJulia, and then you will go iJulia.JupyterLab, and it will bring up the Jupyter Notebook, and you can do Python and Julia in notebooks. You'll have everything right there at your fingertips. Some of the time I for sure want you to be able to use Python for real-time DSP, and that only works in Python, so I'm definitely going to push on that. But if you want to explore Julia, it's just right there too. I don't know if this is exciting or this is depressing, but if you weren't challenged in your life, where would you be? I don't know. Maybe you'd be bored. I would be bored, but maybe challenging is running or hiking or cycling or something like that. I believe you got to do a lot of different things in your life. So this is a hurdle to get over, but I've laid it all out in quite a bit of detail. I'm eventually going to show how you can bring in visual code, or this should say S, not C, VS Code. I use that a lot too. That's another nice tool, but it sits right alongside of all of this install. You won't have to really do anything more. So you have lots of choices and tools. I'm going to try to keep you focused on the notebook here for doing your coding, and then providing a means for getting outputs to attach. So where is this leading to? When you're doing solo projects in a notebook like this, you'll turn the notebook in, print it out through HTML or something. When you're doing homework problems, you will write pencil and paper solutions on engineering paper or something, and then if I say optionally, or you decide to do an exploration to prove that numerically you can get the same answer that you got theoretically, you will attach a sheet behind, say, problem number 1. And then maybe 2, 3, and 4 are all handwritten solutions. But then 5, I say, you can do a simulation for this entire problem. So you might do all of that in Jupyter, or you might just do 1 page of it. So you're going to have kind of like hybrid work that you turn in, where you write it out, but then you also model it and simulate it. Does that sound reasonable? because everything works together. It doesn't work in a vacuum. You don't go to a company. They make stuff. They sell stuff. They don't just write math on the page. But I want you to learn the math part because that's certainly part of what makes the world tick. So that document's right here. I'm going to be tweaking it as we go because, you know, I found a typo, but I'm going to be adding more to it. And I'm going to try to follow those rules. I'm going to put a new Julia combo setup on this tablet. I've done it on a Windows 11 machine that's sitting at home, and that's what I patterned everything after. But I'm thinking about making a video as I install it on here. You know, you've watched the videos on YouTube of unboxing something. You know what I'm talking about? So this would be a video that would kind of take you through the steps of how it goes for me. I didn't have enough time last night, and I could do it right now, but what are the chances are that I'll have a glitch? Pretty good, actually. So, but get started on it and message me on Slack or whatever as you know that unfolds for you. So we'll have projects. This project number 1 is multifaceted. It's on the website right now. Looking at the time here, I guess since I'm saying it's there, where do you find projects? They're right in here. So this is what was done last year. I will modify this. It's entirely Python based and C++ based. I got very creative last year. I said because of my sabbatical experience of having to do a lot of C++, I wanted you guys to try some C++ out. So it wasn't a total success. I'm thinking that Julia would be an option to get speed and do, you know, performance things, but I haven't ruled it out yet. But in this case, though, the setup for doing it was to make a transform domain filtering application that would implement something like this. And the way that it was done was using VS Code and setting up tools on a Windows machine to set up a C++ compiler and the associated tools, and then have the interfaces to Python. So I didn't really leave you hanging because there's an instructable thing still on the website that tells you how to set up all the tools to use the compilers and everything. Maybe I'm going to tone myself down. I'm doing it myself. I've been doing it all summer for this company, and maybe it's just too much to throw at you for one semester. But I do want you to get a lot of exposure because I want you to be able to go in and hit the ground running and just feel like, hey, I've at least seen a little bit of that. I know that tools are out there too, and I feel like tools are something that you have to be able to assimilate on the job. And they don't give you weeks and weeks and weeks. They might give you a new laptop and they say, you got to do this and this. Oh, I don't have anything on my computer. How am I going to do this? You got to just start setting it up and adding tools and configuring and that sort of thing. I have a work laptop and I spent time reconfiguring it because I was running everything in Linux, and because of where I'm at right now, I decided to move from my Windows subsystem for Linux and move it into Windows standalone because of some needs to interface with drivers for SDRs and things. And that's, has anybody ever heard of WSL, Windows Subsystem for Linux? I use that a lot. It's running on this machine right now, and this Pluto notebook is actually running in Linux, and then it's coming up on the Windows side of my Windows Subsystem for Linux to be done that way. And now there's WSLG, which provides graphics in WSL. I have that on a Windows 11 machine, but can't do that here. campus won't allow Windows 11 on campus computers for at least another year. They're not allowed. And where I work in the government, it's not allowed yet either. Does anybody have a Windows 11 machine? I'm just curious.
Yeah, I do. Personal
Okay.
machine, but yeah, we were Windows 10.
Yeah, there's some reasons.
Enterprise.
Yeah. Anybody else have one, a Windows 11? You have what are your OSs? You have a MacBook. I have that. It'll be different to set up on that, but everything works there. But the rest of you have Windows? Okay. I use all of them, but you know, this tablet is Windows, so. But it's hardware and other interfaces. Windows 11 has got some pretty nice new capabilities. So before I do this demo, though, I wanted to keep going through this. So one of the big demo-y things will be using the PC's audio subsystem. And for that, you'll use Pi Audio Helper, and that's included in this new install through Julia. And I've prototyped that out over the past few weeks. On my Windows 11 machine, it works just fine. It might be a little bit, I have to remember how I did it on my MacBook. On my Mac, I use a lot of open source stuff through Homebrew or Brew. If you've got your Mac, do you use Homebrew for anything?
I also use PCs.
Okay, okay. Every operating system, you have little things you have to learn how to do. But I'm going to stay focused on what the majority is using. But since I have a MacBook and I use that a lot, I'll be able to help you. But if you feel more comfortable following the flow with Windows, you know, it'll be up to you how you want to do that. So I won't spend time looking at the real-time audio, but it's very cool with the sliders and things. You're going to be doing things where it's interactive. You'll hear things, you can control things, and add noise in, tune filters. I don't know if that excites you at all or not, but to me it's interactive. It's making something, it's hearing something, so we'll do that. But then there's a capstone project of sorts, and I was thinking of making that be the spread spectrum project. I have a number of projects out there, but that is what this is the rest of the first project, but that project is still here. You can see what last year's project was. It's an adaptive filter project, but this was the project from 2019. This is GPS signal acquisition and tracking. And I've actually been using this project this summer to go off and create a C++ version of this and extending it, and it's going to be used, I don't know in what ways, for the things I'm doing at Augustus Aerospace. But when they asked me to do this, I said, hey, I've got this project. What do I do as a seasoned engineer, and what will you do? You leverage, right? Do you always, do any of you want to start anything from scratch? No, you've got to leverage. You got to leverage anything and everything. I have a leak in my sprinkler system. It's really bad right now. I'm going to have to fix that today, but I'm going to leverage my box of parts and pieces, and I'm going to have to crawl on my hands and knees because it's under a big fir tree. It's a drip system, but I think the puppy we have decided to chew something away, and it's leaking big time, but I'm still going to use the pieces that I bought and hopefully get this solved without having to make 5 trips to Home Depot or something like that. You know, you always leverage though. So this project teaches you about how navigation works with GPS, the history of it. Does this from the get-go sound interesting? Or, I mean, if you've never done GPS before, GPS is pervasive. It's scary because when Russia said we can start taking out any of your GPS satellites, over Ukraine. Did anybody pick up on that when it was in the news? What do you think? Is that a big deal?
Very big.
It's a huge deal because we use GPS for so many things that you don't even know that we use it for. Our cellular network, it's gone without GPS. Time stamping, it's scary in a lot of ways. I don't want to try to make you say you can't drive home safely because you can drive your car, but if GPS goes down, we've got some problems. We have advanced GPS, which I've worked on projects with that before too, make it more robust. But this system is basically how do you acquire the spreading codes, which are unique codes for each of the satellites. And it's based on a model where I was using a low-cost SDR, but the signals are created in Python in a simulation. And then the navigation stuff is, we don't solve the navigation problem, we just get what's called the pseudo range as the result. I'd have another example of how to actually do the navigation using a Kalman filter to track from the pseudo range data. Dr. Plutt's teaching a Kalman filtering class this semester, so if you're interested in how to actually get the full solution, the geolocation part, that's in there. This is more on the inside stuff of how you track the signals from the different satellites. And it uses DSP and a delay lock tracking loop, which is a control system. But it's pretty, the code is all built up here. You just play with it. All the model is built up and it's object-oriented in Python. So that's the transmitter, and then you play with the receiver code. It may look crazy, but I give you almost everything here. You just have a few things to do, and you get to play with it and do some experiments. It'd be like going into the lab, but you're going into a computer lab instead. So, unfortunately, we're not going to get much beyond the end of this chapter, but this is the syllabus. I just have it embedded into this Lecture 1 notes. We've been talking about things all the way along. Office hours. Let's go back here for a second. All of my course websites and my homepage have the link to my office hours, and I will tweak this if need be, but Wednesday is my day to be on campus. Remember, I'm 50%, so I'm not here all the time, and I work from home when possible. I'll be here all these days, all of Wednesdays. I'll be here on Thursdays for faculty meetings. When they occur, they don't always occur. Friday mornings, I'm on Slack audio calls for an hour for each of these students. And that sounds crazy, but I'm trying to flush my pipe. That's the reason why I'm even here this semester, because I could not flush my pipe of all these students. I got rid of only one student over the summer. He went back to Kuwait, finally. Had a lot of problems with students. COVID has been a psychological disease of sorts where people haven't functioned as well as they did before COVID. You may be in that, have had times of depression or just like, what can I do? I mean, we all went through different effects of it, right? It's still lingering on though, but I feel like we're past the worst time of that. But so I spend a lot of time with these people, and I do it virtually mostly. 2 of them are in town. One's in California, the other one's in Omaha, so they're in different time zones even. But you can check that out. But as I've already showed you, Slack is right here. So that's your first avenue of attack. It's convenient. Email, of course, works. I mean, I'm not saying don't use it, but quicker means I think Slack is more convenient for most people. I can schedule a Zoom meeting or Teams meeting if I need to do that too. We'll talk more about technologies with the web stuff, the Julia and Pluto for Python and Julia next week. This is the contract part though. Graded homework assignments, which include numerical things you do in languages, 25%. I expect that to be your own work. I don't say that you can't work together, but you got to turn in your own paper and you have to know what you're doing. Final computer project will be done in teams if you're an undergraduate. And the computer project that's done out of the homework itself will also be in teams. Graduate students, though, I make you do more. I make you work alone. So you have to do your projects alone. Most graduate students want that because they're not here and they want that autonomy. So is that clear? It works well. Trust me, it works well. If you don't trust me, ask somebody that's been in one of my classes before. It works well. Don't be domineering though. If you're on a team, don't do your whole project without your team being involved. The idea of teaming is you can divide and conquer things, but there'll be the final project and then the other project. I think actually I put both projects into this category. There's 2-hour exams. One will be in class. The second one is the week of Thanksgiving. I'll give it out the Friday before Thanksgiving. You get to turn it in on Tuesday before Thanksgiving. So it's a take-home exam. It'll be mostly paper, but it will have some simulation modeling in it too. And then there's the final exam. In these numbers, where you see 2 numbers, what I do is the final exam is nominally 30% with the projects, the big project, and then the end project with spread spectrum being 15%, but then I look at what gives you the best average overall. So if you get a better average with bumping up the project to 20%, taking the final exam down to 25%, you get that. And nobody knows what that is until you take the final. But it's an optimization thing. And why do I do that? It's because some people need all they can get on the final and they're hoping to have a real strong comeback. That 30% is really good for them. Other people have worked hard on their projects and they've done well. Their team projects, if you're an undergraduate, you don't want as much lying on the line with the final. So you'll optimize at that point. It's not a huge deal, but it certainly helps. Does anybody have any questions on that? All of us do these things differently, but this is the way I find that it's worked well for me. This is my 39th year, by the way, so it's not like I'd started yesterday. I've been doing this for a hugely long time, and I exceed your ages in the years I've worked here, so I'll say trust me, but politicians always say that, and that doesn't come true necessarily. The syllabus, last year I tried this experiment of moving these topics right up into here. I believe I'm going to do that again because the DFT and the FFT are so vital in so many things that we do that I just felt like I needed to rearrange it some. So I'll probably do that again, regardless of whether or not I do the C++ FFT. The C++ FFT might turn into a Julia FFT and just see how fast it can go compared to Python. I want to do something with speed because I think that's something that's part of a timing code. That's part of what your life is as an engineer. You got to do things in a certain amount of time. This learning outcomes is an ABET thing, so it's just there for documentation purposes to let you know our accreditation board. We have this on file for all our courses. I added in Slack If I was on a regular browser, this would be a link that would take you to Slack's website. Anything that's in blue is typically a hot link. So your assignment right now is to use the thing I've already showed you, Julia, with Python setup. I'd like you to take that on as you start looking at the first homework assignments too. Then optionally VS Code, and then optionally a Markdown editor, and I'll explain more of that next time. What is Markdown? Have any of you written in HTML ever in your life? Okay, well, Markdown is a simplified HTML is what it stands for, and Markdown is invading our space, whether you know it or not. A lot of tools now have you be able to allow you to write notes and things in Markdown, and Jupyter Notebook is a prime example of that. If I was to go over to here, and Julia Notebooks would be the same thing. You see this code cell, I double click on it, that's Markdown. That's what Markdown looks like. We use hashtags for headers, just like in a web browser. One hashtag is highest level header, 2 is next level. And then Markdown in Julia and in Jupyter Notebook in general allows you to use syntax such as this for equations. And it's taken from an old language that was developed in the 80s called LaTeX. It's a typesetting language. So actually, if I was to do this correctly, what I have to do to make this run on a modern browser, I have to add these tags right here, 2 $signs. It still renders properly here, but another Markdown editor would not render that properly. So what I just added in is another set of tagging, and that's what HTML is. It's all tagging things. And Markdown is tagging, and LaTeX is a numerical typesetting language, which is how my notes are written, is a tagging thing too. So does anybody use Markdown that you knew that you were using it? I'm just curious. I use it a lot now because I use this Typora editor, and if I want to write a Word document and have math in it, or if I want to do something else, I can whip together a Markdown document really fast, and then I can export it to Word, or I can export it to PDF. And the documents on my site are exactly that. They are Markdown documents frequently. This document right here, this was written in Markdown, and I could whip it together. I did screenshots. Your graphics all have to be PNGs or something like that, work best, but and I can put hot links in, you know, this at the end where you get some sample notebooks to try out what you've installed, no problem. Julia modules, it's right there for me. So I like using that. Unfortunately, the editor that was my favorite editor is no longer free. It now costs $14.99. You get 3 seats of it to install across 3 of your computers. You don't have to go that route, but it's just kind of an idea for me. So there's the syllabus. We were through onto this side. What questions do you have right now? I've got 5 more minutes. There is an assignment out there. And I expect all homework to be turned in via Slack. What else did I miss? Well, I'm still rambling here, I forgot. As I go down through here, I talk about when homework is turned in, so read through that. This is pretty straightforward stuff. That's the last page that I missed. I use the website for everything. I will also push things onto Slack, because Slack lets you drop PDFs easily, and I'll push things back to you on Slack on your private channel or DM channel. But I'll also dual list things. I mean, I'll put things on the website. That's kind of my primary, because I'm assuming everybody is going to do that stuff. And we'll start this process of new stuff and review stuff into Signals and Systems next week. And then we take a week off for, no, we don't take a week off, never mind. Thinking I always taught on Mondays, I don't have a Monday class. We never miss a heartbeat until Thanksgiving. We don't take Labor Day off, right? So we do take Wednesday off during Thanksgiving week. So I'm glad for that. You build up momentum and then you get shut down by Labor Day, and it's kind of like you drift back into summer again, and you're not used to working, at school at least. No questions or things you got to know. I'm gonna be going up to lab here momentarily, so I'm gonna be seeing some of you in lab.
So last semester I installed Python the previous way. How would you recommend going back?
That's a good question, and I knew some of you are going to ask that question. They can coexist. I can tell you that much.
I could just go through the new PDF.
I mean, I didn't get a chance to run this guy. Pluto notebooks will be there from the get-go, and you'll see in my model of how that works. This is just tuning things, and this computer doesn't have fast graphics, and I'm doing a recording, but here I'm moving the notch frequency of one of my notches, and I've got a second one. We can do this in Jupyter notebooks for Julia as well, but this one was launched the traditional way. This was launched right from the Pluto notebook. This one was launched directly from the terminal as a Jupyter lab. And you see when it launched up, I could get to Julia. And if you install Julia, you will be able to get it from there. But the way I'm proposing you to do it is entirely different from that. The way I'm proposing, once you follow all of these steps, the cool thing that you're going to have is, and everything will be in one directory. That's another thing that you just say, what do I rip out when I remove this? And whenever you remove apps on Windows, you always think there's some remnant that's going to cause me a headache. Well, this .julia folder holds everything all in one location. It's all right here. A lot of your Python stuff will be in this Conda folder when you get done, and so on and so forth. So when all of this is done and you launch Julia at the terminal, and this is what it looks like for me, I type at the terminal Julia, and it opens up. This is looking at the package manager. I think I don't know if I have a screenshot right there, but at any rate, as I showed at the end down in here, once you finish with all these package installs, you install Julia packages, and then you install Python packages into conda.jl, so it's going into your Julia environment, but it's still Python. When you finally get down here and you go to launch, you will launch a terminal to run Julia. You import iJulia package, which you've installed, and then you run that second line there, and then you're where you're at from last spring. You'll get there all in one swoop like that.
So I can just follow that regardless of what I already have on my current.
Yes. The problem is your computer is going to see multiple Pythons now. It'll see a whole collection of Pythons, but if you want to launch it the way you did before, you would do it that way. If you wanted to follow this, you would do it this way. And the confusing thing for you will be you will have packages installed in your Anaconda, and then you're going to have packages installed in your Miniconda, which is interior to Julia, and there'll be like two separate collections of packages. And if you need to upgrade one or add more packages, you'll have to know which one you're doing it in. The problem is though, if you just launched Jupyter Lab, you'll be able to run, let's say, Python and Julia right from there, whereas if you launch it like I've done here, it'll only access that Python install that's inside of Julia. And I kind of did that for the new people, in that it will not be scattered around, and there have been issues in the past. I'm trying to keep it more localized. And my hope is that with it localized like this, these are the folders right here. And if worse comes to worse, we'll yank stuff out and you can start over again or rebuild it. I mean, that's always, software is just like that. When I say just like that, it gets corrupted and then you end up having to scratch it and start over again. This has a fairly small footprint. I'm gonna, between now and next week, I'm gonna install it on here again. Right now, the Julia that I'm running on here, for example, is running under Linux. And if I start up a new window here, what am I doing that you don't know? As I start up a terminal window and I'm in base, I have to activate a version of Python like we did last spring. You won't have to do that with this new version. And then for me, because of what I've got installed under Linux, I type bash, and now I'm at a terminal window. And if I cd into my root folder there, you can see that, well, let me do it this way. You can see on here, and this is now under Linux, I've got Julia, and I've also got Python and other things scattered around. You will still end up with some stuff scattered in terms of these dot or hidden folders, but all of the meat of what does your code running is in that one .julia folder. And don't get too worried about visibility, but folders that have a dot in front of them, the operating system wants to hide. They don't want you to see them, but we're real engineers, so we're privileging ourselves to go looking behind the curtain. Does that make sense? We're trusting ourselves. We're saying we're grown up about it, we're going to be serious about it, and we're going to get work done this way by going into this .julia folder. You actually won't go inside of it unless you want to put a startup folder in there, and I briefly talk about in that document, but you know where it's at though. That's one of the other things I think that I like about it, is I know where it's all at, rather than mysteriously being hidden somewhere and you don't know where it's at. So, well, I'm done, so I can go up to the lab, and some of you are going to be up in the lab. Let's see who's going to be up in the lab. Yeah. You're going to get tired of seeing me, but you're going to meet Tarant, and he was a master's student of mine. He teaches in computer science here too. He's a very nice personality, very mild-mannered kind of guy. I'm going to stop the video, and this will get pushed up later.